Hey guys, this is probably going to be the most important video of the series because we're going to be looking at the famous Demoivre theorem. Now last time we proved that if we take any complex numbers in polar form and multiply them, then all we have to do is multiply their moduluses and add up their arguments. So in math notation, we'd say any complex number in polar form r1 cis theta 1 times any other r2 cis theta 2 times as many as we want up to Rn cis theta n, that's going to be equal to the product of the moduluses, which is all the r's, times cis of the sum of all the arguments, which is all the thetas. Now what we do to get Demoivre's theorem is we ask what if all these complex numbers are actually the same complex number? Well, that would mean all the r's and the thetas are the same. So on the left hand side we have r cis theta times r cis theta times r cis theta multiplied n times. And that's going to be equal to r times r multiplied n times the cis of the sum of the arguments, which is theta plus theta plus theta n times. Now here we have r cis theta times r cis theta times r cis theta n times. So this is simply r cis theta to the power of n. And so that's going to be equal to r times r times r times r n times, which is likewise r to the power of n, times the cis of theta plus theta plus theta n times, which is simply cis of n times theta. And that's it. That is Demoivre's theorem. But the great thing about Demoivre's theorem is that it works for any number n. So for example, we can calculate the square roots of complex numbers by setting n equal to a half. And that will give us r cis theta to the power of a half is equal to r to the power of a half times cis of half a theta. But of course r cis theta to the power of a half is the square root of r cis theta. So we get the square root of r cis theta is equal to the square root of r times cis of theta on 2. And likewise we can also find the cube root of complex numbers by subbing in n is equal to a third. And that will give us r cis theta to the power of 1 over 3 is equal to r to the power of 1 over 3 times cis of a third of theta. But now this is the cube root of r cis theta. So we get the cube root of r cis theta is equal to the cube root of r times cis of theta on 3. Hold on, that's great and all, but the power of Demoivre's theorem also works for good old simple integers. So let's do an easy example with those first, before we get to roots. So say we want to simplify 1 plus I to the power of 20 times 1 minus I root 3 to the power of 7. Now we could do this the old-fashioned way of expanding and collecting all the terms, but this would take forever. Or we can apply Demoivre's theorem to this 1 plus I to the power of 20 and 1 minus I root 3 to the power of 7. To do this though, we need to convert 1 plus I and 1 minus I root 3 into polar form. But now since we already know how to do that, I'm just going to give us the answers, which is root 2 cis of 45 degrees for 1 plus I, and 2 cis of 60 degrees for 1 minus I root 3. You can check that's correct for yourself. But here we have root 2 cis of 45 degrees to the power of 20 times 2 cis of 60 degrees to the power of 7. Now we can apply Demoivre's theorem to this, which will give us root 2 to the power of 20 times cis of 20 times 45. And then we can do it again for 2 cis of 60 degrees to the power of 7, giving us 2 to the power of 7 times cis of 7 times 60. And now here we simply have the product of two complex numbers in polar form. So we can use this rule from last time to simplify that, which will give us the product of the two moduluses, root 2 to the power of 20 times 2 to the power of 7, times cis of the sum of the arguments, which is 20 times 45 plus 7 times 60. Now the square root of 2 to the power of 20 times 2 to the power of 7 is equal to 131,072. And 20 times 45 plus 7 times 60 is equal to 1,320. Now since we started off with complex numbers in Cartesian form, it'd be nicer to put our answer into Cartesian form as well. And to do that, we convert cis into cosine plus I sine, which gives us 131,072 times the cosine of 1,320 plus I sine of 1,320. And when you plug in the cosine and sine of 1320 into your calculator, you get negative a half and the negative square root of 3 over 2 respectively. So this becomes 131,072 times negative half minus I root 3 divided by 2, which equals negative 65,536 minus 65,536i times the square root of 3. Great, so that means 1 plus I to the power of 20 times 1 minus I root 3 to the power of 7 is equal to negative 65,536 minus 65,536i times the square root of 3. Now that just goes to show you how powerful Demoivre's theorem really is. But that's only the beginning. Now we're ready to look at roots. Say we want to find the cube root of 1 plus I. Now before we continue, remember how when we did the square root of a complex number, we got 2 answers? Well, when you do the cube root, you actually get 3 answers. And if we were doing the 4th root, then you get 4 answers. Basically, whenever you're trying to find the nth root of a complex number, you'll always get n answers back. Now don't worry, I'll explain why this is so afterwards. But anyway, we want to find the cube root of 1 plus I. So first of all, we've got to change 1 plus I into polar form. But we've already done that here. 1 plus I is equal to the square root of 2 cis of 45 degrees. So we really have this cube root of root 2 cis of 45 degrees. Okay, so now what? Well, let's use Demoivre's theorem. First, let's change this cube root into the power of 1 over 3, and so we have the square root of 2 cis of 45 degrees to the power of 1 over 3. Now Demoivre's theorem tells us that this is equal to the square root of 2 to the power of 1 over 3 times cis of 1 over 3 times 45 degrees. And that then simplifies to the 6th root of 2 times cis of 15 degrees. Great, so we found the answer. But remember before how I said there were actually 3 answers? So where did the other 2 go? Now let's go back to our complex plane. We have 1 plus I, which is about here, and we're trying to find its 3 cube roots. One of them is the 6th root of 2 cis of 15 degrees, and that's going to lie somewhere around here. As it happens, the other 2 roots have the same modulus but have different arguments. In fact, these arguments are not just different, they are also equally spaced apart. Again, I'll explain why that's so in a minute, but for now just accept it as fact. Now, a full revolution around our plane is 360 degrees, and since the 3 roots are equally spaced apart, the angle between them must be 360 degrees divided by 3, which is 120 degrees. So one of them would be about here, and this angle would be 120 degrees, and the third one is about here, while these 2 angles are also both 120 degrees. All 3 roots also have the same modulus, the 6th root of 2. Okay, but now we have to find them. Let's look at this one up here. Its modulus is the same, but its argument is an extra 120 degrees bigger. So that's 15 plus 120, which is 135 degrees. So this root here is equal to the 6th root of 2 cis of 135 degrees. And likewise, the other one has a modulus 6th root of 2, but its argument is 120 degrees less. So that's 15 minus 120, which is negative 105 degrees. Cool, so now we've found the 3 cube roots of 1 plus I in polar form, which are the 6th root of 2 of cis 135 degrees, negative 105 degrees, and 15 degrees. You can change these back into Cartesian form by changing the cis into cosine plus I sine, and then getting approximate answers using your calculator. But that's no fun, so we'll just do it for this root. So we have the 6th root of 2 cis of 15 degrees, which is equal to the 6th root of 2 cosine of 15 degrees, plus the 6th root of 2 sine of 15 degrees times I. And if you plug the cosine and sine of 15 degrees times the 6th root of 2 into your calculator, you'll get approximately 1.084 plus 0.29 times I. Anyway, I'm sure you're dying to know why we have 3 roots in the first place, why they're all equally spaced apart, and why all their moduluses are the same. Now it's not easy to explain, so we're going to have to get some more paper. We've lost our Demoivre theorem, so I'll just quickly rewrite it up here. Anyway, when we're trying to find the cube root of root 2 cis 45 degrees, what we're really asking is what complex numbers are cis theta equal root 2 cis 45 degrees when I cube them? Or in other words, what values of r and theta satisfy r cis theta cubed is equal to the square root of 2 cis of 45 degrees? Well, Demoivre's theorem simplifies the left-hand side to r cubed cis of 3 theta. So what we are really asking is for what numbers r and theta is r cubed equal to the square root of 2 and cis of 3 theta equal to cis of 45 degrees. As for the modulus r has to be positive since it is the distance from the complex number to the origin. So that means r can only be equal to the 6th root of 2, which is why all of our roots had the same modulus. However, the same cannot be said for the arguments, and here's why. The cis function is made up of cosine and sine functions, which means that it has some of their unique properties. In particular, sine has the property that sine of x is equal to the sine of 360 plus x, which is equal to the sine of 720 plus x, and so on. And cosine also has this property as well. So the cosine of x is equal to the cosine of 360 plus x, which is equal to the cosine of 720 plus x, etc., etc. But because cis is made up of cosine and sine functions, it's also going to have this property. Another way to think about it is with the complex plane. So if you have any complex number that has an argument in this direction, then adding 360 degrees or 720 degrees or whatever will just rotate it through full revolutions around the complex plane. But it will still end up facing the same way it started, so it's the same thing. Anyway, back to our case of cis of 3 theta is equal to cis of 45 degrees. Cis of 45 degrees can also be written as cis of 360 plus 45, or cis of 720 plus 45, or we can even go the other way around and go cis of negative 360 plus 45, and so on. Okay, so now we can get rid of the scisses, and we'll get 3 theta is equal to 45, or 45 plus 360, or 45 plus 720, or 45 minus 360, and so on. And now watch what happens when I divide everything by 3. We'll get theta is equal to 15 degrees, or 15 plus 120, or 15 plus 240, or 15 minus 120, and so on. Now this gives us 15 degrees, 135 degrees, 255 degrees, and negative 105 degrees, etc., etc. But notice here that we got an extra angle, 255 degrees. So what happened? Well, let's try and find our angle 255 degrees in our complex plane. So we start rotating anti-clockwise from the real axis like this until we reach here, at which point the argument is 180 degrees, or half a revolution. But to get to 255 degrees, we have to keep going. However, the moment I start going past 180 degrees, the angle flips over and becomes negative down here. In fact, going forward 255 degrees is exactly the same as going backwards 105 degrees. So our 255 degree solution is actually the same as our negative 105 degree solution, which means we can just cross it out. This is why we only get 3 solutions when taking the cube root. It's because when you divide the argument by 3, that allows you to add or subtract 120 degrees. But if you try to do it for 240 degrees or more, you just repeat the answers you got from adding or subtracting 120 degrees. And this is also why the angles are always equally spaced apart. When you cube the number the 6th root of 2 cis of 135 degrees, it's the same as cubing the 6th root of 2 cis of 15 degrees, except you do an extra revolution around the complex plane. But you still end up facing the same way. If that doesn't make sense, don't worry, it'll become more clear as time goes on. But just remember that whenever you're trying to find the nth root of a complex number, there are always going to be n roots, they are always going to have the same modulus, which is the nth root of r, and they are always going to be equally spaced around the complex plane. Let's do a last example, and that can do for this video. So say we want to find the 9th roots of I. So by our list up here, we can expect to find 9 answers, which will all have the same modulus, and should all be equally spaced apart around our complex plane. Now to use Demoivre's theorem, we need to convert I into polar form. And now I know this to be cis of 90 degrees, but you can just see this from the complex plane because it's about here. So the modulus is obviously 1, and this argument is 90 degrees. So now we have the 9th root of cis of 90 degrees, which equals cis of 90 degrees to the power of 1 over 9, and by Demoivre's theorem, this equals cis of 10 degrees. Let's go ahead and plot cis of 10 degrees in our complex plane, like this. Now the other roots are going to be equally spaced apart in our plane, and since there are 9 of them in total, that means the angle between each of them must be 360 divided by 9, which is 40 degrees. So that means our roots are going to be the cis of 10 plus 40, which is the cis of 50 degrees, and we can put the 50 degrees back in and get cis of 50 plus 40, which is the cis of 90 degrees. And now notice that we've got the cis of 90 degrees back, which we know is simply I. Now this is fine, it just means that one of the 9th roots of I is going to be I itself. Or in other words, I to the power of 9 is equal to I. Anyway, let's go back on track. So we have the cis of 90 plus 40, which is equal to the cis of 130 degrees. And we also have the cis of 130 plus 40, which is the cis of 170 degrees. Wait, stop! Notice that if we add 40 to 170 degrees, then we're going to get an argument that's bigger than 180 degrees. Namely, it will be 210 degrees. But as we saw from before, once you go beyond 180 degrees, the angle switches back to the negative side. So at this point we have to stop, and we start subtracting 40 degrees. So we have cis of 10 minus 40, which is the cis of negative 30 degrees, and now plugging this back in, we get cis of negative 30 minus 40, which is the cis of negative 70 degrees, and again we get cis of negative 70 minus 40, which is the cis of negative 110 degrees, and then we get cis of negative 110 minus 40, which is the cis of negative 150 degrees. And now again, notice that if we were to keep going, we'd get an angle that's less than negative 180 degrees. But that would simply flip over to our positive side in the complex plane. So like before, we stop here. Cool, so now we have all of our 9th roots of I. And if we put cis of 10 degrees back on our list here, we can see that there are exactly 9 of them as expected. And as promised, that's it for this video. Next time we'll be looking at the geometry of complex numbers as vectors. See ya!